Right now, in this high-tech factory, 20 tons of banana blossoms are 3 degrees away from becoming worthless. One temperature mistake, 6 hours of work lost, an entire production line stop cold. This isn't farming. This isn't cooking. This is industrial precision, where timing is measured in seconds and failure costs thousands. Welcome inside a factory you've never seen before. Banana blossoms, the purple flower that hangs at the end of every banana bunch. In traditional markets, they're hand-cut, sold fresh, and used within hours. But in modern food manufacturing, they're processed at massive scale. Blanched, vacuum-sealed, frozen at -35 degrees Celsius, and shipped worldwide. This facility operates nonstop, 8 tons per day, 12-hour shifts. The raw material must arrive within 4 hours of harvest. That window is critical, because unlike bananas, the blossom oxidizes the moment it's cut. Enzymes activate instantly. The clock starts ticking. The factory has exactly one shift to transform fresh blossom into shelf-stable product. And that transformation depends on decisions made in seconds. From start to finish, the process has 6 major stages. But only 3 contain decisions that can shut everything down. Let's break them down. Stage 1. Reception and pre-cleaning. Workers strip away the outer purple petals, exposing the white edible core inside. Stage 2. Manual separation. Each blossom is broken down layer by layer. The core is isolated. Stage 3. Oxidation control. The first critical decision happens here. Stage 4. Blanching. The second decision point. Stage 5. Rapid cooling and vacuum packing. Stage 6. Blast freezing at industrial scale. Everything flows in sequence. But stages 3 and 4 are where technical control separates success from total loss. Let's examine what's really happening at each decision point. Critical decision 1. The moment a banana blossom is cut, enzymes called polyphenol oxidases start reacting with oxygen. You've seen this with apples. The brown discoloration when you leave a cut apple on the counter. Banana blossoms do the same thing, but much faster. In industrial practice, the separated blossom must enter an acidulated water bath within 15 minutes. 15 minutes. Not 20. Not 10. Here's why that window matters. If the blossom enters too early, workers rush. Quality drops. Unremoved petals contaminate the batch. If it enters too late, oxidation has already begun. The white core turns brown. And here's what most people don't know. This browning isn't just cosmetic. It's an enzymatic cascade that, once started, cannot be reversed. Not by acid, not by freezing, not by anything. The product is already lost. From an engineering perspective, this is a race against chemistry. The solution is a 2% citric acid bath. The low pH denatures the enzymes. Oxidation stops immediately. But this is where process stability is tested. The factory monitors 3 variables at once: pH level, water temperature, and immersion time. If the pH drifts above 2.5, enzyme deactivation is incomplete. The product will brown during storage. Rejected. If the water temperature drops below 10 degrees Celsius, the acid's effectiveness decreases. If it rises above 15 degrees, bacterial growth accelerates. Either way, the batch fails quality control. And the immersion time must be exactly 12 minutes. Too short. Enzymes remain active. The blossom browns within days. Too long. The core absorbs excess acid. The final product tastes sour. Unusable. This control exists to ensure every blossom entering the next stage is chemically stable, visually white, and ready for heat treatment. The factory uses automated pH sensors and temperature controllers, real-time monitoring, instant adjustments. Because this decision, made in a 12-minute window, determines whether the next 8 hours of processing succeed or fail. One deviation here and 20 tons become animal feed. Critical decision 2. Now the blossom moves to blanching. Thermal processing at high-tech industrial scale. Blanching has 2 functions: final enzyme inactivation and microbial reduction. The target temperature is 95 degrees Celsius. Immersion time, 90 seconds. This decision is often underestimated, and that's a mistake. Here's what's happening at the molecular level. At 95 degrees, the remaining heat-resistant enzymes, peroxidase and catalase, are permanently denatured. These enzymes survived the acid bath. Only heat kills them. But there's a margin of error, 3 degrees. If the water temperature drops to 92 degrees Celsius, enzyme deactivation is incomplete. During frozen storage, the product degrades. Texture breaks down. Color shifts to gray. The entire batch is rejected at inspection. If the temperature rises to 98 degrees Celsius, the blossom tissue itself starts breaking down. It becomes mushy. Structural integrity is lost. Premium product becomes industrial waste. 3 degrees. That's the difference. From start to finish, the blanching conveyor moves at fixed speed. 90 seconds of immersion. No variation. But here, small deviations create massive losses. The factory uses a continuous blanching system. Water is heated by direct steam injection. Temperature is monitored at 6 points along the conveyor. If any sensor detects a 2-degree drop, steam flow increases automatically within 1 second. If the temperature exceeds 96 degrees, cold water is injected immediately to bring it down. This level of automation exists because human reaction time is simply too slow. At 8 tons per day, the factory processes approximately 550 kilograms per hour. That's 9 kilograms per minute moving through the system. A 3-minute temperature deviation affects 27 kilograms of product. At premium pricing, that's hundreds of dollars lost every 3 minutes. In industrial practice, this is where mass production meets precision control. And the blanching decision directly determines success in the next critical stage, rapid cooling. Critical decision 3. After blanching, the blossom exits at 95 degrees Celsius. It must reach 10 degrees Celsius within 4 minutes. Exactly 4 minutes. This cooling rate is absolutely critical. If cooling is too slow, residual heat continues cooking the product from the inside. Texture degrades. The blossom becomes soft, unsuitable for premium packaging. The factory uses a 2-stage cooling system. Stage 1, ice water immersion. Temperature, 2 degrees Celsius. Duration, 2 minutes. Stage 2, forced air cooling on a stainless steel conveyor. Duration, 2 minutes. Why this specific approach? Rapid immersion in ice water creates thermal shock. It stops the cooking process instantly. The temperature drops from 95 to 40 degrees in seconds. But prolonged immersion causes a problem: water absorption. The product gains weight. Excess moisture leads to large ice crystal formation during freezing. Those crystals rupture cell walls. The texture is destroyed. From an engineering perspective, this is heat transfer optimization balanced against moisture control. The factory monitors core temperature using infrared sensors. Non-contact measurement. Real-time data fed to the control system. Once the product reaches 10 degrees Celsius, it moves directly to vacuum packing. No delay. Vacuum packing removes oxygen. This prevents any remaining oxidation during frozen storage. The vacuum level is set at 99.5%. Sealing temperature, 180 degrees Celsius for 0.8 seconds. If the vacuum level drops to 98%, oxygen remains. Oxidation can still occur over 6 months of storage. The product arrives at the customer already degraded. If the sealing temperature is too low, the package doesn't seal completely. Air leaks in during transport. If it's too high, the plastic melts and contaminates the product. The entire package is rejected. This control exists to ensure 6-month shelf stability. From harvest to vacuum-sealed package, the entire process takes exactly 6 hours. And every decision made in those 6 hours is visible in the final product. The vacuum-sealed blossom enters the blast freezer. Temperature, minus 35 degrees Celsius. Freezing time, 45 minutes. This rapid freezing creates microscopic ice crystals. Small crystals mean minimal cellular damage. When the customer thaws the product months later, the texture is preserved. Slow freezing, like in a home freezer, creates large ice crystals. These rupture cell walls. The product becomes mushy and loses all commercial value. The result of every upstream decision is visible at this final stage. If oxidation control failed, the product is brown instead of white. If blanching temperature was incorrect, the texture is wrong, too soft or too firm. If cooling was too slow, the product is overcooked, unusable. If vacuum packing failed, oxidation occurs during storage. The product degrades before reaching the customer. Each decision compounds. One error creates a cascade of failures. The factory's quality control laboratory tests every single batch. Color measurement using spectrophotometry. Texture analysis using penetrometers. Microbial testing for shelf life verification. Rejection rate, less than 2%. That's the result of precision control at every critical decision point. 3 decisions, 3 variables, 3 points where everything can go wrong. Oxidation control, 15-minute window, 2% citric acid, 12-minute immersion. 1 mistake and the batch turns brown. Blanching temperature, 95 degrees Celsius, 90-second immersion, 3-degree margin. 1 deviation and texture is destroyed. Cooling and vacuum packing, 4-minute cooling window, 99.5% vacuum. 1 error and shelf life collapses. This is modern food manufacturing, where precision meets massive scale, where 1 wrong decision stops an entire production line, and where technical control transforms a perishable purple flower into a shelf-stable product that travels halfway around the world. That's the reality inside a factory you've never seen before, where flowers become frozen perfection, and where 1 wrong decision changes everything.